Alright guys, welcome back to the YouTube channel. Today we are going to look into Newton's law of viscosity, but before we dive further, let's remind ourselves that a force is a push or pull that causes an object to change its motion or shape. A force can either be contact force or non-contactless force, right? And our force is measured in Newton, which is mass times acceleration, right? And the SI unit is Newton. Velocity is the rate of change of an object's position with respect to time. So velocity is equals to distance over time, which is equal to, or the SI unit is meter per seconds, meter per second, right? So what is the relationship between force and velocity? We need to understand that force causes acceleration, in which in turn changes an object's velocity. That is, this acceleration in force, right, it causes a change in velocity. Before we jump into the question of the screen, I'm going to explain to us how we derive the formula for viscosity under the topic Newton's law of viscosity. Let's dive into that. Alright, so our dynamic viscosity, right, is a measure of fluid resistance to deformation under shear stress, right? So, and our shear stress, tau, this is mu, the previous one I drew is mu, then this new one is tau. So, our shear stress, which is tau, if you remember, is equal to force over area. That's force applied over the area of the surface, right? Also, we'll be needing our velocity gradients, in which we derived from this cylinder, right? So when a fluid flowing between two parallel plates, so these are the parallel plates, we have the stationary plate and the moving plate. So we have a fluid flowing in between them here, right? So one plate is stationary and one plate is moving. When a fluid flows between two parallel plates, one moving and the other stationary, the velocity varies linearly with the distance from the stationary plate. So this is it. The V and F here, right, is our velocity and force. Remember that I said that acceleration affects velocity, a change in velocity. So we have a fluid in between these two plates, which is our moving plate and stationary plate. The distance between the two plates is our Y, right? Therefore, our velocity gradients is equal to, right, change in velocity over change in distance. So remember that these two guys are together. We cannot separate them when we begin to solve. They are attached together. So here our V is the velocity of the, and our Y is the perpendicular distance from the stationary plate, right? For a Newtonian fluid, we know that shear stress is directly proportional to our velocity gradient, which is change in V over change, let me write this up, over change in perpendicular distance, change in velocity over change in perpendicular distance. So when we introduce the constant of proportionality, which is our dynamic viscosity, it becomes shear stress is equal to dynamic viscosity multiplied by our velocity gradient, which is change in velocity over change in perpendicular distance to the stationary plate, right? So from here, we'd also discover our viscous force, right? Remember that shear stress is equal to force over area. So if I go ahead looking for our force over area is equal to our dynamic viscosity times our velocity gradient, y over y, velocity over distance, right? Change in velocity over change in distance. So making our f the sort of formula, we say f is equal to all of what we had initially multiplied by our a, dynamic viscosity times area times our velocity gradient over change in perpendicular distance, which is our gradient, which is our velocity gradient, right? So here is our viscous force, formula for viscous force, right? And here is where we talk about our shear stress being directly proportional to our velocity gradient. So solving ahead and making our dynamic viscosity the subject formula, we derive dynamic viscosity is equal to, remember I said we are going to always treat this guy as together. We're never going to split them, right? So let's assume it is an x. Our dv over dy is equal to an x. Like let's make it an x. Let's do it somewhere here. So it's going to be tau is equals to dynamic viscosity times x, right? So I'm dividing both sides by x, so it becomes this, right, it becomes dynamic viscosity is equals to tau over x, right? Remember I said I'm dividing both sides by x, so x cancels this, so this is how I got this. So now let's substitute back our original value for this, right? So it's going to become this, it's going to become our shear stress over our velocity gradient, right? Shear stress is equal to tau times this dy over dv, or on the other hand, leave it as what is in this circle. Okay, so some might be like, when do I apply this and when do I apply the one down? So if you are going to apply this one, let's assume in a question you are given velocity gradient. Let's say we are given velocity gradient to be 1, right? So now we know that we don't know our dv, we don't know our dy, so we just know, okay, the gradient being joined together is 1. So all we just do is we say shear stress over 1, right? But if in the case where you are giving your dynamic, you are giving your perpendicular distance to the stationary plate to be 1, then your velocity to be 2. So you know we know the answer to be 1 over 2. So we can always change it to 2. We can always apply it here, knowing each side. So we know that it is 1 over 2. But case whereby we just know that velocity gradient is 1, right? All we just have to do is mind our business and just stick to this formula, right? Let's go on. So I don't know if that made sense to you. Let me go around it again. Let's assume we are given a question whereby our velocity gradient, right, whereby our velocity gradient, right, which is dv over dy is equal to 1. So now I do not know the value for dv individually. I don't know the value for dy individually. I just know the value for dv over dy is 1. So in that case, I am to use this formula. But case whereby you are giving the value of dv differently and you are giving the value of dy, so in that case, let's assume our dy is 2 and our dv is 3. So I can say 2 over 3 because I know them individually. But case where I don't know it individually, you apply this formula. So that is when I apply this formula, when I know each part differently. So I'm going to revert my step now and continue with what we were doing. Okay, so we finally agreed, right, that dynamic viscosity is equal to our shear stress, right, over our velocity gradient, which is dv over dy. So let's derive the SI unit for our dynamic viscosity. Alright, so to go ahead and discover our SI units for dynamic viscosity, which is this guy, we go ahead to solve on by simplifying the equation into this shear stress times we have dy over dv, right? You know what I just did? I just turned this upside down because this is divide. So if I'm going to multiply, it's going to become inverse of that. So let's begin to simplify things. So we know our dynamic viscosity is equal to, so shear stress is force over area, in which it is Newton, over meter square. That's our area, over our velocity. So velocity, as I spoke about earlier in the video, is meter per second, right? Then our change in y, which is distance, is going to be in meter, right? So by the time we simplify this, it becomes, let's say, equal to, we have n over meter square times m, right? So by the time we multiply what's down there, become s over m. So let's begin to cancel through. Cancel this, cancel this. So this is how we derived our dynamic viscosity. The SI unit is equal to Newton times seconds all over meter square. Alright, so now let's solve this question. So we have been told that two parallel plates are 0.003175 meter apart. So we know our y, right? So this would be, this would be our distance y, right? The lower plate is stationary and the upper plate moves with a velocity. So we know this is our v, velocity v, 1.524 meter per second. Then our stress, this is our tau, shear stress, is equal to 2.394 Newton per meter square. Is needed to maintain the upper plate in motion. find the viscosity of the fluid contained between the plates. All right, before I go ahead, I forgot to mention that we also have kinematic viscosity, which is equal to our dynamic viscosity over our density. All right, guys, so let's go ahead and solve for the SI unit for kinematic viscosity. All right, so we know that our dynamic viscosity is equal to Newton per second over meter square. Density is equals to mass per volume, right? So first of all, let's simplify our dynamic viscosity. So we need to know that our Newton is equal to kg meter over second square. Right, so let's input into this our Newton here. Newton is equals to kilogram times meter over second square, right? So let's input that into the equation above. So we go ahead and say dynamic viscosity is equal to kg, right, times meter over second square. So what we did right now is right here is our Newton itself, right? So multiply by our seconds from that equation above all over our m square. So this is literally this equation here, right, that we just repeated. So now let's cancel this, cancels one of these, so we are going to fall out. It's going to become kilogram times meter over seconds. Now for this guy at the moment, it is divided by, so our meter square is going to become 1 over meter square, you get, so meter cancels one of these also. Therefore our dynamic viscosity is going to be equal to kg, it's going to be equal to kg, I want to make sure it does not look like an S, it's going to be equal to kg over seconds times meter. So to find our kinematic viscosity, remember it is dynamic viscosity over density. So for our kinematic, reverse step, let's change ink, reverse step, therefore for our kinematic viscosity, now some of you might be wondering, why did I simplify to kilogram? It's because our density is mass over volume. Density is kg per meter cube, so I needed to simplify in such a way that things can cancel each other. So from here we apply this, which is equal to our dynamic viscosity, which is kilogram, I keep making that mistake, kilogram over seconds times meter, right, multiplied by, so our density is going to be inverted, right? So density is mass over volume, mass over volume, kg over volume. Remember I said it's going to be inverted because here it is fraction. So kg cancels kg, we lose 1 over our m and cancels this guy. So therefore our kinematic viscosity, let me just write it here, the SI unit for our kinematic viscosity is meter square per seconds. Yeah, so that is that about that. I needed to touch it before I get to omit it. So let's go ahead and just solve the main question we are supposed to solve. Alright guys, so we are told to find our viscosity, which is our dynamic viscosity. So remember that we said our dynamic viscosity is equals to shear stress over our velocity gradient, which is dv over dy. Remember our v is velocity and our y is our perpendicular distance, right? Okay, so therefore remember I told you that there are some cases where we'll be able to simplify to this extent. So it's going to be equal to shear stress is equal shear stress multiplied by our dy over our dv. So now why am I able to do this is because I'm not giving velocity gradient. If I was giving velocity gradients in this question to be 1, I'm going to apply the previous formula, which is this guy. But since I'm not giving velocity gradient, I'm going to apply this one because I know each value for each parameters, which our y is 0.03175 meter and our velocity is 1.5 meter per second. So let's go ahead and apply our formula. So we know our shear stress to be 2.394 Newton per meter. So you don't really need to stress with your SI unit since we already solved our SI unit. Let's just solve our mathematical question. So 0.003175 over what's our dV, which is 1.524. So let's punch that into our calculator and see what we get. So which is equal to 4.99 times 10 raised to the power minus 3. And remember our SI unit for dynamic viscosity, which is raised to the power 2, right? And at the same time, we could go ahead and invert our step 1 to 3, which is going to give us 0.00499 newtons times seconds per meter square. Alright, so before I say we are done, let's assume this question we're not told to find kinematic viscosity, right? But let's assume we're being told to find kinematic viscosity, right? And we know that the fluid and let's assume that we are being told that the fluid in this question is water, right? And therefore we know that the density for water is equal to 998 kg per meter cube, right? So let's assume we know that okay, the fluid here was water. We are being told the fluid here is water. Then look for the kinematic viscosity. All you just need to do is remind yourself that kinematic viscosity is equal to our answer, which was 0.00499, right, over our density of water, which is 998, right? So whatever answer you get, our answer SI unit is going to be meter square per second from what we derived earlier here. So this is literally how to find what's it called, our kinematic viscosity, if we're being told that the density the fluid is water and the density of water is this. So yeah, this is how it works. All right guys, make sure you subscribe to the YouTube channel. Thank you very much for watching. Peace out and bye.